will be covered for your test one on this Friday. Okay, I already sent to you the video. I hope that you learn from that. Okay. Oh, today is full house 40. All right, good. Okay, because of test, right? Okay. Let's look about induction. So what is really the induction? So induction is happen because when we induce some current or some voltage, right, to some what we call it some coil. Okay, we can call it coil. So this coil is produce some okay. Muhammad Akib, can you mute your mic?
Oh, sorry.
Okay, good. All right. Um, so inductance, that's mean is a phenomena where EMF is induced, right, in it by a variation of current either in the circuit or neighboring circuit. So when we have some voltage, right, that induced into some coil or some what we call it uh, the conductor, so it will produce some magnetic flux. Okay, so to increase the inductance, the conductor can be formed into a loop or coil. Okay, right. Current through one loop produce a magnetic field that encircle the loop, right, like a figure A. Okay, so as the current increase, so the magnetic field expand and cut all the loops. Okay, so this one we look into that. All right. Okay. Variable reluctance sensor. Okay, in this topic, there are two types of sensor that you will look at. So the first one is a variable reluctance sensor. Okay, all right, the concept. Okay, in the magnetic circuit, reluctance we call it R is a measure of how the circuit oppose the flow of magnetic flux. So also we know the variable inductive transducer. Okay, like like you said there earlier, right? So this is I hope that you can see that. Okay, this is your coil, right? So you inject some voltage, right? Or of course, when you inject some voltage, that means they will have some current I, right? Okay, so this current, right, will produce some magnetic flux over here. Okay, and then you will have some movable core here, right? So this one movable core will move up and down, right? Or maybe you can have from the right to the left. Okay, so this movable core you can put it into some object that are you going to measure, for example, right? So so that's mean you're going to measure this displacement of this object. So you can use this concept, right? Variable inductive transducer. So if a permeable core move through the coil, okay, the inductance increase where the value of inductance depending on the position of core. Okay, so that's mean if the core move up, so the value will be different with the core if move down. Okay, so the formula for the inductance. So now we have the L. Okay, inductance. So the formula is L is equal to N squared over R. So R is the reluctant. Okay, R is reluctant. So reluctant is depending on the L. Okay, L of this movable core. Okay, and divided with nu and nu naught over A. A that's mean the area, right, of that core, right? So that's mean maybe we can draw a 3D here. So this one the area and so on. Okay, the area, right? So L that's mean how um that's mean the length of the movable core and so on, right? So A this cross section area. Okay, and every core, so we'll have a core permeability here, right? So if you look at that, that's mean when the R is increased, so that's mean your L, right, inductance, so you will got it this decrease. Okay. Alright. Okay, let's look example 9.1 here. Okay. Where is my alright. So the inductive transducer is used to measure the displacement. Given the core permeability nu C equal to 100, okay. So if you look at this one, this is the coil, okay, and then you will have the core permeability. So we'll have the nu C here, okay, all right. So what happen is when you inject some current, right, to through this coil, so it will produce some magnetic flux here, okay, right. So then this is your uh, armature permeability, right? This one that's mean you will put it, or maybe you want to measure some object, right? Some mass here, right? So this is you have the arm, okay, permeability with a nu A equal to 100, and of course the air also have the air permeability, nu air equal to 1, okay. And then you got it, the coil equal to N equal to 500, and R is the rate equal to 2 cm, right? R that's mean for the, yep, for this one, all right. Okay, for the radius of your core permeability, and the small r is equal to this one, right? This core permeability you use is something like what we call it hollow one, right? So it will generate some magnetic flux, right, to this one, okay. And your core is like the square core, like here. Maybe I can show it to you here. Where is it? Okay. Uh, if you look at this one, I'm going to use to show it to you. Okay, like this one, right? Okay, you can have a square, right, or U-shape core, right? This one, and this is your target, right? So your target will move up and down, so you can measure this what we call it is direction, right? Okay, like here. Okay, like this one, core U shape, and this one you have the iron or metal mover, so you can measure the displacement here. Can a lot of these uh, uh, variable reluctance sensor, right? So you can look at in, you can type this one, you can go to image and so on. Okay, all right. So far, do you have any question? Okay. Yes, yes. Uh, is it the L is depending on actually um, the core, right? That move into the coil is here. Okay, alright. Yes, yes, yes. Correct. Yeah. Okay. All right. And what is L? So what's L? Okay. Okay, we are here. Okay, determine the reluctant R and inductant L. Okay, so you're going to determine the reluctant first, and then from the reluctant you can find the R and the L, the inductant. Okay, so where the gap equal to D equal to 0, that's mean the distance, right? You don't have a distance. That's mean this amateur, right, that close with your core permeability here, and then after that you got the distance equal to 1 mm. Okay, so let's look this what we call it the solution for that one. So first of all, you need to gather all the information from this question. Okay, so we got it is mu c, okay, equal to 100, and then you got it a new A equal to 100 also, and then you got it a new A, okay, equal to 1, and then your N, that's mean your number of loop, okay, equal to 500. Okay, alright. And then what else do you got it? You got it is R equal to 2 cm, so you convert it into meter, and then you got it a radius for small r 0.5, you convert it to meter 0.005, and then the thickness for T equal to 0.005 meter. So if you look at this one, okay, so when you have an hollow there, right, so it will produce the area, right, is a square area like here. That's mean is a 2r and also a t here, okay, this is the length, okay, right. So now we have gathered all the information, and step 2, so what you need to do is you want to find the reluctance first, okay, the reluctance first, and then after that you can find the inductance, okay. So reluctance is depending on, that's mean how many core that you have right now. You have the core here, okay, and then you will also have the air permeability here, and also you will have the arm permeability here, okay. So that's mean uh, R, you're going to have the R, we put it a core, okay, RC here, and then you plus with RA, and then you plus with R arm, okay, here, alright. So for D equal to 0, so of course you only have the R core plus with R arm, okay. So you don't have any air here, right? So for the R is depending on L, your L, the value of, sorry, and then mu naught, and A. Okay, right? So A, because D equal to 0, so you don't have any air here. Okay, so from this one, you can find your L here. Okay, so L equal to N squared over total of reluctance. Okay, right. So this is the concept, and then step 3. So you can find this one. So first of all, you find the R core. So that's mean your L. Okay, your L. That's mean if you look at this one, your L. Okay, is given to you. Okay, this one. Okay, the L is 2 pi R divided with half. Okay, all right. 2 pi R here, you divide with half here, and then you do nu c and nu naught pi squared. Okay, A pi squared. Why? Because you use the core permeability is type of hollow right here, so it will have this one pi r squared here. Okay, right, you can look into that, right. So and then after that you calculate, you got it, the reluctance for core is 6.37 times 10 power of 6 here, and then you calculate for R arm. So R arm is equal to this length, okay, that's mean 2R, the length equal to 2R here, okay, right, 2R and plus R here, and then area is equal to 2RT. 2RT, that's mean this area, okay, 2R and you time with T here, okay, this one. That's why I told you the area is depending on the cross section area, right? Okay, and then after that the line equal to 2r, and then you calculate, then you can get it is 6.37 times 10 power of 6. Okay, for the r air is equal to 0 because of there is no length, right? Because there is no distance. And then you can get it the r total from summation of r core plus r arm, and then you got this value. After that you can get it this inductance. Okay, 19.6 millihenry. Okay, h is henry. Okay, so far do you have any question about this one? Ada persoalan tak? Macam straightforward lah, I think. Okay, do you have any question? Ada persoalan tak? Okay, no? No question? Can I proceed? Boleh? Okay, good. Alright. And the next you're going to find the reluctance for D equal to 1 millimeter. Okay, so I think this step is quite clear. So you only find the air gap. So L equal to 2D here. If you look at this one, this one is quite clear. So D, because you have the D is here, 2D here, D, we're going to find the air gap here. Okay, right, so D equal to 1 mm, 1 mm. Okay, so 2D, 2 times 0.01, and then you put a new air 1 and new naught 14 and pi r squared, right? Because the air is also have the area for in the circle, and then you got it this you got it this one, the value for reluctance for air, and then you total up for core plus arm plus air, and then you got this value, and then you will find inductance. So if you compare with this one, right? So what happened is the inductance will be decreased. Okay. So why? Because the reluctance, right? So it will increase. So that means the inductance will be decreased. So this is the concept. If you going to measure the certain object or certain mass that when you use the concept of variable reluctance sensor. Okay, so for your test one is about, I think it's about some theoretical about it. So you need to be able to draw, be able to discuss, be able to describe the concept of this variable reluctance. Okay, all right. Okay, right. And the other type of this inductance, or we call it inductive transducer, is the linear variable differential transformer. So this one is LVDT. So LVDT is comprised of a coil former, right? So if you look at this one, you will have some form, right, in term of what we call it, normally in term of hollow, right, this one. Okay, and then you will have some two coil here, we call it is a primary. Okay, and then this one is the secondary. Okay, so what happened also, you will have some movable core, right? So this one you can put it in some mass or some object that are you going to measure some displacement. Okay, so the first coil here, so it will excited with an AC, right, current, and this one, and the other two coil that you will measure this output from here. Okay, so let's look what is the output happen. So the core, okay, at the center, this one, you will get it, the output will be what we call it, will be 0 lah, right? There is no output here. So when the core, how was it? Okay, when the core move to section 1, okay, This one is section 1. We call it the for the secondary coil here. We move it, right? So you will see that um, this one, right, for section 1 here. Okay, this one when at the center, and then when the coil moved at here, you will got it at the section 1 output. You will got this kind of graph. Okay, right. Okay, and then when the coil move at the section 2, so you got it this kind of graph. Yep. So it will inverse a polarity with each other. Okay, all right. So when at the center, that's mean there will be no output here, right? Okay. So this primary that's mean the excitation, that's mean you will inject some what we call it, the AC voltage, okay, to here. So this is the AC the output waveform, right? So when for example you go to the right, so you will get it, your voltage will be increased a little bit and so on, right? So when it go to the left, so it will decrease. Yep, here we got some voltage, but it will inverse a polarity here. Okay, right. Okay, this is the simple circuit lah. So when you have your core and also primary and secondary, and this circuit, if you want to convert it into DC voltage, I think you still remember when you do the lab one, right? For electrical lab. Oh, sorry, that's one is for previous experiment. So this one is we want to convert from AC voltage to DC voltage. That's why you use the uh, rectifier. Okay. So there are two type of LVDT. One is linear and one is the uh, rotary. Okay. Okay. There are some part that I not covered yet. So I think let's look some example here. Okay. So far, okay. Do you have any question? Boleh? Is there always has the R arm? Yep. R arm is like your target. It depending on your object. Okay. Like I mentioned you before. So this is your object that you going to measure, right? For example, your object is target the iron. Okay. Alright. Any more question? Ada lagi soalan? Uh, you can look in others example or the image at here. Last time I have do some bookmark. Yeah, this one. Yeah, this one. Okay. Alright. So if you look at here, right? So this is your inductive sensor, right? So it use the concept of variable reluctance sensor. So what it do is it will produce some magnetic flux. Okay. So when your object, or we call it your target matter, right, is near to your sensor, right? So if we got it is some voltage, right, it will be almost zero. Okay. And then when it is go far from your sensor, you will got it this kind of voltage. Okay. Right. Yep. Okay. All right. Any more question? Ada persoalan lagi? Do you have any question? So far okay? Boleh? Okay tak? Guys? Sengap saja ni. Tak blur-blur lagi ni. Okay, okay. Good. Alright, okay saja, right? Okay. Alright. Let's look this example. Okay. This is the example of the calculation, right? Okay, for the LVDT, right? So, LVDT, right? So, as we know that for the LVDT or inductive sensor, we should know about the transfer function first, okay, for transfer function. So, of course, the transfer function is give you to you, for example, millivolt over millimeter. So in this case, what is this output? So this output will be millivolt, right? For the ability, we're going to use the ability to measure the displacement, linear variable displacement transducer, okay? So, and then the input will be some millimeter, right? Some small displacement, and then you will got is some output, okay? So this is the transfer function, or sometimes we call it is sensitivity, right? Okay, resolution, this one. So for example, this one, it put it is 40 millivolt per millimeter. Okay, a linear variable differential transformer has a stroke length of plus minus 150 millimeter, and it produces a resolution of 40 millivolt per millimeter. So determines the LVDT maximum output voltage. Okay, so this one is, I think, you will use back on what you will learn on the first on the second chapter, I think. Okay, so let's look. First of all, this is your ability starting point, all right, from zero, and then it can go up to 150 millimeter here. Okay, and then of course your ability can go, that's mean, okay, can go right for 150 millimeter, and also it can go left for minus 150 millimeter. Okay, alright, this one, do you understand about it? Okay, if you look at here, the concept is, yeah, it can go down, right, or go right, and then it can go up or go left. Okay, so that's mean it will give you the positive and negative value. Okay, boleh faham okay, now the first is determine the maximum output that it can measure, right? So maximum output here is 150 milli. Okay, it's quite simple. So you will have the 150 millimeter here, so you can find the output here. So maximum output 100 millimeter, you time with 40 millivolt over millimeter. So this one, you will got it, the value is uh, equal to 6 volt. Okay, so of course you will have the positive, right, going to the left, and you will have the negative here. Okay, faham tak? Clear? Do you understand about it? Any more question? Clear? Any more question that you're going to ask? Ada apa-apa soalan? No? Clear? Okay, good. Alright, so this is for question 1. Question A. Okay. B, the output voltage when the core is moved to 120 millimeter from its null position. So in null position, that means is 0. So now it moved to 120 millimeter. Okay. Right. So now this one is quite simple. So 120 millimeter. So now you time with 40 millivolt per millimeter. So now you got it is what? 120 times with 40. Okay. You got it is 4.8 volt, right? Okay. So that's mean the maximum it can produce is 6 volt, and then for 120 millimeter, so it will produce 4.8 volt. Okay, so the range is 6 volt minus 4.8 volt. Okay, right? Okay, so we can use this concept. For example, your core move to maybe 100 millimeter to 100 millimeter. Okay, so you can find the range of this one. Right, done. Okay, and the core position from center when the output voltage equal to 3.7 volt. Right. Okay, so now you're going to find number 3. The core the core position, right? So at which position it will produce for 3.75 volt. So this one is quite simple. So X you time with 40 millivolt per millimeter is equal to 3.75, and then you can get your X. This means 3.75 you divided with 40. Okay, then you will got it is 19.75 millimeter. So that's mean at 3.75 volt, so the displacement is at 19.75 millimeter. Okay, boleh faham okay. Alright. And then number 3 and number 4, voltage change is ask you to find the voltage change from plus 80 and minus 80, right? Displacement. So you can get it the summation, right? Like said, you got it this one. Like is move from 0 to 80 millimeter and minus 80 millimeter. So it asks you to find what is the voltage range for this one. So you can add 80 plus 100, 80 plus 80, so 160 millimeter. So you time with 40 millivolt over millimeter here. So 160 times 40, so you got it is 64 volt, right? So this is the range, right? It will move to here and to here, right? Okay, so voltage change for this one. Okay, right? The change in output voltage when the core is moved from plus minus 80 to plus minus 80 displacement. Okay, so take a look this example, right? And this example, we use the concept of this operational static characteristic again. Okay, so you will look at the performance analysis. So I think you should remember this one. Okay, so we're going to look at when you have some accuracy, some error again. Okay, so because this example, if we use this concept. Okay, all right. Do you have any questions so far? You see, I'm using a old laptop, right? This one is 2010. Okay. All right. Do you have any question about the example of this LVDT calculation? Why is done saying okay? Any example? Any question? No. Okay. Ada persoalan? Siti? Tak ada? Okay. Is it clear? Is it clear, right? Okay. All right. So we have finished covers for this chapter for the FVDT. Okay. So others of application is like a servo force balance. So like I said you before, this is the LVDT. Okay, LVDT. So you can attach to any object or any target that you're going to measure, okay, displacement, right? Okay, and other topic is what we call it, piezo. Uh, do do I have cover this topic before? Saya dah cover dah topik piezo ni. Ada tak? So, dalam kelas. Anyone can answer that? No.
No.
Oh, wow. Oh, Aini. No. Wow. Okay. Alright. Good. So we got about 10 more minutes. Okay. Alright. Piezo transducer, for the test one is about only the theory. Okay. So you can go through. So first of all, let's look the piezoelectric effect. So what is the piezoelectric effects? Is based on the quartz crystal. It's based on the word piezins. That's mean when you that's mean to press. Okay, so you will have some piezo material here. So for example, quartz or barium titanate or tourmalines. Okay, I don't know about this material. So when you give some pressure about at this material, so it will produce some voltage. Okay, some voltage right to here or EMF. So for example, like this one, you give some pressure to this crystal. Okay, so I don't know whether is it a crystalline crystal or not. Okay, so it will produce some voltage. And the good thing about this piezoelectric, right? It can react as the sensor, right? This one we call it as the sensor lah, because we give some physical input, right? And it also can react as the actuator. Okay, right. So let's look this. This about the theoretical. So when you give some pressure, it will give you what I call it voltage, and then after that, if you don't give the pressure, it will release that material. Will release back. It will give you some different voltage. This is the type of effect lah. So whether you can force it from this way and order this way. Okay. In order to use a displacement sensor, so you can use this concept. So you can put it as some rigid, and then after that you give some forces here. So the displacement is depending on 1 over k you time with the force that you apply. So k is the crystal stiffness. So any piezoelectric material will have some stiffness here. This is a good thing about the piezoelectric material. I think we have looked this one before on the accelerator topic, right? So one of these example of the accelerator accelerometer sensor is used the piezoelectric concept. So this is the others application of piezoelectric for this force sensor and pressure sensor and the accelerometer. Yeah, we have discussed this one. When you give some pressure here, you knock out. So the mass, the seismic mass, so it will push this crystal and then you will get this output from here. Okay. And for the pressure sensor, is also same method. You give us some forces here and then we just produce some output here. Okay. Also with the force sensor. Okay, all right. Okay, what's else? This about the theoretical, all right? This one is not be covered for you lah. Okay, this one, right? This one is too detailed. Okay, this is quartz. Why we use quartz? Blah 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 lah. This one. Okay. In terms of typical application, you can use it for combustion monitoring. This one is the pro and con. Yeah. Direct and converse piezoelectric effect. Okay, like I mentioned you before, piezoelectric transducer is a good thing because you can use it in two ways. First of all, you can use as a sensor. So sensor, that's mean the effect we call it direct effect. Direct effect, that's mean you give the direct forces right? Direct input to this piezo, right? Piezo material. So what happened is when the piezo material, right, experience compression, okay, right, and then it will give you the uh, um, what we call it, the output voltage, right? And then when you stretch it, right? When you stretch, yeah, you stretch it, so it will give you some voltage, but it will different polarity. And it also can react as the actuator. Actuator, that's mean if you give some voltage, right, to this piezoelectric material, so this material will expand, right? We expand, right? So and then if you give the different polarity, right, it will compress. So my question is, what of these example of this application of this piezoelectric effect? What is the example? Right? Apa example-nya? Maybe you can write in the chat. Okay. Aini, ya Aini. Tadi kata no. Aini, what is the example Aini? That use this direct and converse piezoelectric effect in the real life. Right now, it's happened. Wait. Wait. Okay. Right. What's L? Aini Fazlini sengak pula ya. Okay. What the other example? Pressure sensor. Apa dia? Okay. Other example is right now is happen right now is mic and what is it? Mic and speaker, right? So your mic is the sensor, is the input, right? So inside the mic, that's mean microphone. Yeah, it's not the MIKE. Okay, so inside the microphone we'll have a piezoelectric material. So what happened is your voice, right? It will give the pressure to that material, to that piezoelectric material. Okay, that is the microphone. As the sensor, you use the concept of directly effect. And for the speaker, that's mean when you give some audio to the mic and so on, then it will convert to some voltage, right? And then it will go to your OM amplifier and so on. And then your OM will generate some voltage, and then that voltage will trigger out your speaker. So inside that speaker will have the piezoelectric material also. So that that material will expand. That's why you can hear the voice from the speaker. That is the concept. Okay. That is the example. Okay, clear? All right. This is direct and converse effect lah. This one. Okay, like I mentioned before, it's a good thing about this sensor and actuator. So you can for the piezo, you can convert actuator, and also you can use for sensor. All right. So this other application lah. So you can read by yourself lah. This one. So piezoelectric topic is yeah, that's it about some theoretical only lah. Okay. All right. So far, do you have any question? Ada apa soalan? Your test 2 will be covered filter, inductive, and also piezoelectric. Okay, transducer. All right. If you have any question, you can ask me, you can WhatsApp me directly. So I will try to answer it. Okay. Sorry guys, this week I got some problem with my laptop. So if you want to contribute your Max laptop or Mac Pro laptop, maybe ikut it for me. Siti, yeah, Siti is quite kaya lah dia ni. He use iPhone, Max Pro.
So,
Yes.
for Isoelectric, there will be no calculation question in the test.
Oops, maybe no.
Okay.
Okay, right. It just in term of what you call it, theoretical, but LVDT will have some question, calculation about it. But the piezo electric transducer, you need to be able to describe the about the concept, right, or theoretical, how the piezoelectric can be used to apply for force sensor, pressure sensor, and so on, and what is the direct. This is the what we call it, common question lah, from the previous semester. Okay, Faris can donate. Okay, good. Okay. All right. I think that's it for our class for today. Okay. Is it okay? So I will see you again for your uh, test too. Okay. I just want to have some feedback. Is it okay for the test two we conducted as test one before? That's mean you will got it, the question through the email, and you will submit it to e-learning. Is it okay?
Okay.
Okay. Alright. I test at what time? According to the timetable that I got it is, I think, at 9, yeah, at 9 p.m. Right. I will send you the guideline for the test too, like I've sent it to you before. Okay, for the test one. You share example test two. Okay, all right. Please remind me on that one. Okay, all right. I think that's it. Now at 10, yeah, at 10. Okay, that's it for today. So thank you for your attendance. All right. Have a nice day. All right, and have a nice test too. Okay. All right.
Thank you,
Thank you.
sir.
All
Thank
right.
you, Doctor.
Okay. Welcome.